Now, this is the last section, which is kind of an application or the properties of solids we are going to study. And more correctly, we will be studying about electrical and magnetic properties of solids. Now, in this particular section, first we will start, of course, with electrical properties. We can classify solids on the basis of their electrical conductivity. And perhaps you know the meaning already. The one is first one, conductors, and they will have obviously very high electrical conductivity. Now, conductivity is measured in the units of per ohm per meter. In physics, usually they call this per ohm as Siemens. So you can write that unit as Siemens per meter also. And as we know, metals and electrolytes will fall in this category. The second type which we study are opposite of conductors, that is insulators, bad conductors of electricity. The conductivity is extremely poor. You can see here with the values 10 raised to minus 20 to 10 raised to minus 10. All the non-metals except the graphite as an example, and all molecular solids will be the bad conductor of electricity, insulators. The third among them, between them, is semiconductors. Now they will have conduction in between moderate of insulators and conductors. If you compare the values, you can see 10 raised to minus 6 to 10 raised to 4, where in conductors you can see the lowest value was 10 raised to 4. Very famous metalloids like silicon and germanium function as semiconductors. Now we will go in details of these conductors, insulators, semiconductors on the basis of solid state. And we will see how chemistry explains the behavior of these three. We use all these things in physics, of course, but they don't give you much explanation. And the explanation which physics give you is basically coming from chemistry only. In physics, perhaps if you have heard something known as band theory, it has come from chemistry. And we are now going to study what is known as the band theory over here. So we can explain the conduction of electricity by simple meaning that whenever any substance conduct electricity, it will be through the movement of electrons. Metals can conduct in solid state. Metals can conduct in molten state also. Now, this conductivity depends upon how many valence electrons are present per atom. For example, if you consider sodium atom, sodium has 3s1 as the outermost orbital. That means there is only one extra available valence electron is present. On the other hand, if you take magnesium, the outermost orbital has 3s2. So it is a pair of electron which is present over here. So as the sentence says, conductivity will depend upon how many valence electrons per atom are present. From this sentence, we can gather that sodium will have lesser conductivity than magnesium. Magnesium will have lesser conductivity than aluminium. So the last sentence is of great importance. Now we explain this conductivity, as I said, using molecular orbital theory. Molecular orbital theory suggests that whenever two atoms combine together, they produce molecular orbital. Now, in case we remember the things which we did last year in 11th standard, let me just explain a small part of it so that you understand what is this band theory concept. So imagine we are combining two atomic orbital, and we used to draw a diagram if you remember. Here there is one atomic orbital. On this side, there is another atomic orbital. And when they combine, they create equal number of molecular orbitals. Out of that, we used to call this orbital as bonding molecular orbital. This is anti-bonding molecular orbital. This is what we did in 11th standard. This is for combination of atom number 1 and atom number 2. Now imagine that we convert this diagram into a slightly different format so that, this concept is clear. So imagine this is the way we are combining, and my atom number 1 and atom number 2 are both present here, only on one side, not the way it is written here. So this will create one bonding orbital and one anti-bonding orbital. Imagine I introduce two more atoms in this, such that now more orbitals are created. Like this, if I keep on adding infinite number of atoms in the whole thing, naturally we will get large number of orbitals created. So this whole diagram can be simplified in this manner, wherein we have half the part as bonding molecular orbital, half the part as anti-bonding molecular orbital. Imagine an example of, let us say, sodium, which has only one electron per atom. So if there are one electron per atom, both the electrons will be filled in bonding orbital. Same way here also, all electrons will be filled in bonding orbital. Here also, electrons are filled over here. This means anti-bonding orbital will be completely vacant. These, what you see here as a highly simplified diagram, is known as a band. This is what they call as band theory. So this is the lower band which is filled with electron. This is the upper band which is empty. This is a case for group 1 element. Imagine a band theory for group 2 element. In group 2 element, there are 2 electrons outermost. So if there are 2 electrons in the orbital, 2 will go here, 2 will go here. That means at that time, your orbitals will be entirely filled. So let it be ABMO or let it be BMO. Everything will contain now electrons. So both the bands, upper and lower, are filled with electrons. If this much part is clear, I will go ahead. These diagrams are not given anywhere in your books, so I'm giving this additional one. Anything you want me to repeat out of this? How bands are produced? Bolo.
So for group 1 only bond BMO.
Lower, yes, correct. Lower one will be filled, upper one is empty.
And group 2 both.
Group 2 both. Imagine group 13. Group 13, what will be the case? In group 13, you have NS2, NP1. So here we will have a case wherein this will be the filled entire orbital. So this is going to be
then half
ABMO and BMO of which one? NS. और इसके ऊपर और एक ऑर्बिटल रहेगा, that will contain p orbital. उसका half filled रहेगा. Everyone understood this? What is the meaning of this part?
Perfect. So that will be only BMO, no?
BMO, yes, lower one of that. So इसका BMO, इसका ABMO फिर से empty है. We need to know these three cases: sodium or group 1, group 2, and group 13 aluminium boron. This has been explained in your GTB, but without any diagram. They have given paragraphs on sodium, magnesium, aluminium. Aluminium is not there in GTB, these two, but no diagrams are given. Those who want can take a screenshot. Or I want you to remember right now where BMO is filled, where ABMO is empty. In group 1, BMO is filled, ABMO empty. Group 2, both are filled. In group 13, something else happens. NS orbital entirely filled, BMO, ABMO, NP half is filled.
So what about 14? Full?
Same way. Again, 14 onwards, 14 is going to be silicon. So there the things are going to be different. We will see that. Now I'm going in details of band theory after this, so that we can explain.
PS half filled.
Which one?
PS and NP3. If it is NP3, it will be like
Similar things will happen. Something like this only will happen. Somewhere it will be half filled, somewhere 1/3, because
So at
NP has
NP6 it
six
will be
solid.
full, right?
Yes, correct. NP6. So NP6 it will go for which one? Inert gases. Correct. But that is not in solid state, so we don't consider that. So please now read this paragraph. Whatever I have explained, based on this, look at this para. We, instead of now calling them as just BMO, ABMO, bonding, anti-bonding, in terms of electricity, they call it as conduction band and valence band. So we will now explain these terms in detail on the next slide. Let us take up conduction band. Conduction band will be the highest energy band, and this will be formed by the outermost orbitals. Conduction band may be partially occupied or partially vacant or completely vacant also. Electrons in conduction band are mobile. They can move from here to there over entire solid, and they can conduct electricity when potential difference is applied. Compare it with the second one, valence band. Valence band will have a lower energy, and this valence band will contain electrons which are bound to the respective nuclei. So in other words, you can imagine valence band is same as our bonding molecular orbital, which is containing electron. Conduction band will be the upper one, which is vacant right now. So basically उनका concept कैसा है वो दिखाता हूं, लेकिन एक पहले energy gap वाला concept है वो भी देख लेना. Then if you want, I will come back. Energy difference between valence band and conduction band is called band gap. This value of band gap, what they call it size, मतलब actually वो energy difference रहता है, decides whether electrons will be promoted from valence band to conduction band or not. So if band gap is too much large, then promotion becomes impossible. That time they call that as forbidden zone. If band gap is small, electrons can be promoted just by supplying electricity or thermal energy or radiation. So coming back to our diagram, which we saw here on the whiteboard, now I can name this. So for group 1, if I label this, then group 2 and group 13. What we see in reality is something like this. In group 1, you are going to have this as the it is as the bonding orbital. This is completely filled. In group 2, this entire thing will be filled. Group number 13, this will be filled. This might be partially filled. So which are these orbital? This lower one is the valence band. This is the conduction band. This is valence band. I hardly can distinguish. I'm just imagining half of it. Here, this is valence band. This is somewhere conduction band. So if valence band and conduction band are quite nearby, we can transfer electrons from valence band to conduction band. Here in this case, we can transfer electrons from valence to conduction. This is for group number 1, group number 2, group number 13. Now imagine if in some case, if my conduction band is this way and valence band is like this. So this is the filled valence band and this is the conduction band. Now you can see the transfer is to be taking place after an energy gap. This energy gap, what you see here, is what they termed as band gap. Now here if you see, the band gap was there, but we consider it as 0. क्योंकि बैंड गैप ऑलमोस्ट है ही नहीं, क्योंकि दोनों ऑर्बिटल सेम ही है, यहाँ पे बैंड गैप ज्यादा है। तो अगर बैंड गैप इज लीस्ट, so I can say band gap for metals, it's going to be least compared to metalloid compared to non-metal. तो नॉन मेटल में बैंड गैप इतना ज्यादा होगा कि इलेक्ट्रॉन जंप कर ही नहीं सकता। वी कॉल दैट एज बैड कंडक्टर ऑफ इलेक्ट्रिसिटी। इज द कंसेप्ट क्लियर सो फार? एनी डाउट? Those who want can take a screenshot. I'm going to show proper diagrams also later after this. Yeah.
So an exchange of electrons,
हाँ,
what
एक
happens
मिनट,
then?
exchange नहीं हो रहा है. We supply voltage. So when potential difference is applied, electrons are going to go from one point to another. So imagine यहाँ पे इस अल्कली मेटल को हम लोगों ने यहाँ पे कनेक्शन कर दिया है, and this is our connection made for potential difference. So now electron, so आप लोग कैसे स्कूल में इमेजिन करते थे, ये आपका कंडक्टर है, फिर आपने इसको ऐसे वोल्टेज अप्लाई किया और आप बोलते थे इलेक्ट्रॉन्स आर गोइंग टू गो फ्रॉम नेगेटिव टर्मिनल टू पॉजिटिव टर्मिनल, ये सब आप जो बोलते थे, इसका ये साइंटिफिक एक्सप्लेनेशन है. सो आर यू थिंकिंग कि इलेक्ट्रॉन के एक्सचेंज में यहाँ कुछ हो रहा है? दिस इज जस्ट अ कंडक्शन.
So it's just a moment, like
Yes,
of the
yes,
electrons.
they call it as drift of electron, mobile nature of electron, because potential difference is applied.
So sir, this valence band and this conduction band is just imaginary. Like there's no
Absolutely,
actual
absolutely,
band.
absolutely. There are some energy gaps and all in molecules, they are correct, लेकिन वो ऑर्बिटल के सेंस में है एक्चुअली. ये हम लोग जो बोल रहे हैं, these are our orbitals. So electrons are present in orbitals, molecular orbital, which are just named as valence band, conduction band. जैसे यहाँ पे देखा तो परहैप्स ये 2s ऑर्बिटल है, ये 2p, या फिर सिलिकॉन में देखेंगे तो सिलिकॉन में ये 3s है और ये 3p ऑर्बिटल है. यहां से यहाँ पे जंप करना डिफिकल्ट है, इम्पॉसिबल नहीं है. तो इसलिए सिलिकॉन का कंडक्टिविटी इन बिटवीन है. यही डिफरेंस हम लोग और ज्यादा इमेजिन करेंगे, डायमंड परहैप्स, तो ये गैप बहुत ज्यादा होगा, तो इलेक्ट्रॉन उतना जंप नहीं कर सकता. वी कॉल इट एज नॉन मेटल. सो एनर्जी, ऑर्बिटल का एनर्जी में कितना डिफरेंस है, दैट डिसाइड्स द होल प्ले ऑफ कंडक्टिविटी. I will show you the official diagrams also.
Sir,
Bolo.
the graphite is a non-metal, but it's the
Correct.
conduction. na?
Because of
The-
hybridization, because graphite has sp2 hybrid carbon, so there is pz orbital ka electron available for conduction. On the other hand, diamond is sp3 hybrid. All the 4 electrons are involved in bonding. No free electron available. इसलिए diamond is bad conductor.
So in this you don't consider band energy,
See,
na?
क्या है,
Band gap.
कैसे होता है कि एक चीज को एक्सप्लेन करने के लिए अलग अलग थियरीज देते हैं लोग. तो बैंड थियरी इज वन वे ऑफ एक्सप्लेनिंग. यूजिंग हाइब्रिडाइजेशन, फ्री इलेक्ट्रॉन, अनदर वे ऑफ एक्सप्लेनिंग. some wherever it is applicable, suitable, we use that theory. Theory is just a thinking of scientist, which we call as theory. Theory का मतलब ही यही है कि we know the phenomenon, उसको कैसे एक्सप्लेन करते, कोई ए साइंटिस्ट इस तरह से सोचेगा, बी साइंटिस्ट दूसरी तरह से सोचेगा. जब तक दोनों करेक्ट है, वी एक्सेप्ट बोथ द थिंग्स. So this is what I imagine for group 1, group 2 and group 13 perhaps. So यहां से देखो 3s से अगर 3p ऑर्बिटल में सिंगल एटम जंप कर रहा है या फिर मल्टीपल एटम्स जंप कर रहे हैं, तो दिस बिकम्स द बैंड. ये बैंड में क्लोज प्रॉक्सिमिटी ऑफ ऑर्बिटल्स आर देयर, दैट्स व्हाई ड्रिफ्टिंग ऑफ इलेक्ट्रॉन्स इज पॉसिबल. अभी हम लोग तीनों को कंपेयर करते हैं. देखो ये वाला है मेटल, तो मेटल में आपके पास फिल्ड और एम्प्टी है, या फिर फील्ड ऑफ एम्प्टी में ओवरलैप हो गया है. सो इन दिस केस, नाउ सी द ऑब्जर्वेशन, वैलेंस बैंड एंड कंडक्शन बैंड आर वेरी क्लोज और दे ओवरलैप. ओवरलैप कहां पे दिखाया था मैंने? ग्रुप 13 में आपको ओवरलैप दिखाया था डायग्राम में मैंने. सो द बैंड गैप बिटवीन देम इज वेरी लेस एंड इलेक्ट्रॉन्स कैन इजीली जंप फ्रॉम वैलेंस बैंड टू कंडक्शन बैंड. Compare it now with semiconductors. Gap is small between them. So band gap is small. Electrons may jump, but show less conductivity. In physics, they call this as intrinsic conductivity. Intrinsic, that is the inherent nature. We can change their conductivity by a process called doping. Adding impurity in them, we can change the conductivity. That leads to N-type and P-type semiconductors that we are going to study now in some time. Third is insulators, where the gap is too much large. I hope this concept is okay. Those who are pure HSC students, this entire lecture, what we are doing today, is cancelled from the 25% part syllabus. So boards में ये नहीं आएगा आपको. JEE and NEET, of course, it is not cancelled. Now, this is one set of examples I'm giving. I'm not going in details of it at all. These are merely examples of oxides. और उसमें से कौन से ऑक्साइड्स इंसुलेटर है, कौन से मेटालिक है, मतलब कंडक्टर है, it is merely a list. This is given in one of the JEE books, but never asked in any exam so far. Not there in NCERT, GTB भी तो mention भी नहीं है इसका. Just treat it as an additional information, I will say. Don't give too much value to this, but it should be there in your reading somewhere. Now we take up individually semiconductors in detail, because insulator में कुछ study करने जैसा है नहीं. Conductors are quite normal, so we study now semiconductors. Intrinsic semiconductor, that means at room temperature, their conductivity will be extremely low. आपको लगभग ऐसे लगेगा कि ये इंसुलेटर जैसा ही है, इतना कंडक्टिविटी पुअर रहता है. तो प्रैक्टिकली हम लोग सिलिकॉन, जर्मेनियम को एज अ कंडक्टर यूज नहीं कर सकते. दिस कैन बी इम्प्रोवाइज्ड बाय एडिंग सम सुटेबल इम्प्यूरिटी. अभी आप ये वर्ड इम्प्यूरिटी से थोड़ा समझ गए ना. हम लोग को हमेशा रियल लाइफ में लगता है इम्प्यूरिटी मीन समथिंग रॉन्ग थिंग एडेड, वी डोंट नीड इट. हियर इट इज नॉट सो. इम्प्यूरिटी का यहाँ पे मीनिंग है we add something which will change the property of the matter. That process of adding impurity in science is called doping. Now this doping can be done by two types of elements, either electron rich atom or electron deficient atom. The example we are considering can be either silicon or germanium. These impurity will create defects in them. जैसे हम लोगों ने कल फ्रेंकेल डिफेक्ट, शॉर्टकी डिफेक्ट, वेकेंसी डिफेक्ट देखा था, वही टाइप के डिफेक्ट्स इसमें भी होंगे. एंड थैंक्स टू द डिफेक्ट देयर कंडक्टिविटी इंक्रीजेस. सो लेट अस स्टडी द थिंग्स इन देम. दिस इज गोइंग टू बी द ओरिजिनल पिक्चर ऑफ सिलिकॉन. हियर इफ यू कंसिडर एनी सिलिकॉन, it has 4 valence electrons, 1, 2, 3 and 4. To the neighboring silicons, 1 electron is being shared and simple covalent bonds are produced. If you consider the hybridization, actually it undergoes sp3 hybridization. So group 14 में आपको सबसे ज्यादा सेमीकंडक्टर मिलते हैं, जैसे सिलिकॉन एंड जर्मेनियम. Go through this para before we now go for doping after this. Now observe this one. Here we are having phosphorus, and phosphorus has 5 unpaired electrons. So there are going to be 1, 2, 3, 4 and 5. So out of the 5 electrons, 4 electrons are involved now with bonding with silicon. 5th electron has remained extra. That is not able to bind with obviously anybody. That electron becomes the conducting electron. Such type of semiconductors are called N-type semiconductors. The word N-type indicates negative because electron is gone in conduction. So it is called the negative type semiconductor, N type semiconductor. Go through this. We are going to only use group 15 elements here, phosphorus or arsenic, which can properly gel with silicon and they can leave one electron additional for conduction. Any doubt, or we go ahead for the next type of semiconductor? I think in physics or in those who are doing electronics or something, you must have done this part already. Much more detail than this. Next is the p-type semiconductor. We are now taking here an element boron, which is group 13 element. You can either use boron, aluminum, gallium. Group 13 element will have only 3 electrons for bonding. So silicon can give its electron and transfer an hole over here. That means this is a vacancy for electron. Now this will create what is known as the positive type semiconductor or p-type semiconductor. Because in electronics, they consider the hole as positive charge. Electron is a negative charge. So absence of electron is taken as the positive charge. Any doubt in these three things properly understood? P-type, N-type semiconductors. Physics में हुआ आपका chapter ये?
Yes, sir. Yes, sir.
Yeah, you must have done then greater detail. ये तो एकदम लल्लू है, बच्चों का काम है ये.
So
If
we
you
are
are
not
done,
done yet.
okay. So applications of these extrinsic semiconductors. The most basic device we study in electronic semiconductors is diode. And diode is obtained by joining a p-type with n-type semiconductors. That's why it is also known as PN-type diode, PN junction diode. There are, of course, different type like Zener diode and other thing, light emitting diode. So many other types are there. But basic diode is obtained by joining N and P type. Then you have next level called transistors, where N type is sandwiched between two P type, or P type is sandwiched between two N type semiconductors. So that's why you have two types of transistors, NPN transistor, PNP transistor. Transistors have absolutely different applications, a world of applications. इसमें से बहुत सिंपल एप्लीकेशन याद दिया है जो सभी को समझ में आ सकता है. That is radio signal and audio signal detection. But of course, they have lot many works in electronic industry. Solar cells are going to use photodiodes, and modern different semiconductor devices, they use, instead of pure silicon or pure germanium, you can see they use a mixture, gallium arsenic, zinc sulfide, cadmium sulfide. They can be taken, then doped with the impurity and converted as a extrinsic semiconductor. Semiconductor is just a world of science. The entire electronic industry, computers, hardware, mobile phone, entire electronic thing is just concerned with these semiconductors. We don't, of course, go in more details in chemistry. The entire physics is based on that only now. That's what we call modern physics. We have finished with electrical properties. We come to now the last part of the chapter, magnetic properties. Now we know the reason basically for magnetism. Basic reason is due to the presence of electrons. More correctly, not just electron, but unpaired electrons. If electrons are paired, magnetism will not be there. So magnetism basically is measured in terms of magnetic moment. And that is due to two types of motions of electrons. First movement is orbital motion. The electron revolving around the nucleus creates a magnetic moment. Electron spinning around itself creates a magnetic moment. Joining these two magnetic moments, we get the final resultant magnetic moment. Now, this magnetic moment which we consider is basically nothing but a small loop of current. So when a charged particle, means electron, is revolving, it creates current, which further creates magnetic moment. So if you remember, in D block and F block elements, we had heard that it creates spin magnetic moment and orbital magnetic moment. This magnetic moment is measured in the unit of Bohr magneton. One Bohr magneton has this particular value. Usually they don't ask this in exams, but it is given in the book. Now, magnetic property or substance classification of magnetism is of 5 types. Number 1, paramagnetic, diamagnetic, ferromagnetic. ये तो आपने सुना ही होगा. But we have 2 more types called antiferro and ferrimagnetic. So we are now going to study these 5 magnetism and check how they are created, produced, and basically what are the examples in them. So we first begin with paramagnetism. This is the definition. In my all short notes, my first point is the definition, although I'm not labeled it there. Important words I have made in red here. Substance get attracted to the magnet or even a non-uniform magnetic field from weakest to the strongest region. They are called paramagnetic substances. Perhaps we know the reason already. It is due to presence of one or more unpaired electrons. We had already done in D block, F block topic, all these things. So they are magnetized in a magnetic field and in the same direction. If magnetic field is removed, they will lose the magnetism. Most important for your exams are examples, especially if you are a NEET student or CET student. They ask you to choose the odd one out from this. I have given in the list here whatever is there in all the books, GTB, NCERT, JEE books, सबका collection करके मैंने यहाँ दिया है, तो आपको और example ढूंढने की जरूरत नहीं है. Next is going to be diamagnetism, opposite of this. So in diamagnetism, substance will be repelled. आप example first point compare करोगे तो ये exactly opposite point आपको दिखेगा. The magnetic field is repelled. Then this is basically due to weakly magnetism created, but in opposite direction. So अगर external magnetic field, let us say north to south जा रहा है, तो ये substance का magnetic field south to north जाएगा. They will cancel each other. That's why they don't show any magnetism. Condition, as we said earlier, this is due to paired electrons. And due to the paired electron, magnetic moments are cancelled. Few examples here: titanium oxide, water, NaCl, benzene, so many. Go through this, both the paragraphs. Any doubt you can ask me. Magnetism चालू हो गया आपका फिजिक्स में टॉपिक.
So that we finished already, I guess.
ओके नहीं, 11th का भी है मैग्नेटिज्म, 12th में भी.
11th का.
हाँ, 12th में भी अलग है मैग्नेटिज्म. दैट्स व्हाई मैग्नेटिज्म इज बोथ द प्लेसेस. चलो, नेक्स्ट वन इज फेरोमैग्नेटिज्म. फेरोमैग्नेटिज्म एक्चुअली इज अ कंसेप्ट ओनली डन इन फिजिक्स. केमिस्ट्री में इसका ज्यादा यूज नहीं होता है, बट इन दिस टॉपिक दे हैव केप्ट इट. हियर substance will be strongly attracted by the magnetic field, and not only strongly attracted, but it will be a permanent magnet. So once they are magnetized, they are permanent magnet. So basically for layman's term, अगर आप कोई किसी कॉमर्स स्टूडेंट को पूछेंगे कि मैग्नेट क्या है, तो जो वो बच्चा मैग्नेट बोलेगा आपको, दैट ही इज रिफरिंग इज फेरोमैग्नेट. जब हम लोग साइंस नहीं पढ़ते तो हम लोग को एक ही चीज पता होता है, मैग्नेट, नॉन मैग्नेट. तो उनके लिए मैग्नेट का मतलब होता है फेरोमैग्नेट. पैरामैग्नेट ये नॉन साइंस पर्सन को पता ही नहीं होता है. अभी पेपर इज डायमैग्नेट, लेकिन जो आपको स्टेशनरी शॉप में एक छोटा मैग्नेट मिलता है खरीदने के लिए, वो होता है फेरोमैग्नेट. पैरामैग्नेट यूजुअली हम लोग को कहीं मार्केट में मिलेगा ही नहीं. दैट इज यूजुअली अ केमिकल सब्सटेंस. अभी ये मैग्नेट कैसे फॉर्म होता है, इसका एक थियरी है जो आपको फिजिक्स में डिटेल में करेंगे. इट्स कॉल्ड डोमेन थियरी. अभी इस डोमेन थियरी का लॉजिक कुछ इस तरह से है कि यू कैन सी हियर डोमेन थियरी. This one part you can see here, which I'm marking. This is perhaps a group of atoms having some magnetic moments. So ये जो वेक्टर्स आपको दिख रहे हैं ये सब मैग्नेटिक मोमेंट्स है ग्रुप ऑफ एटम के. तो ये एक डोमेन, ये दूसरा डोमेन, ये थर्ड डोमेन, फोर्थ डोमेन, लाइक दिस. So when domains are present, they are absolutely in a random manner. When we apply this external magnetic field, the domains get arranged exactly aligned with the oriented with the external magnetic field. This is what you call as ferromagnetic substance. अभी ये थियरी बहुत साल तक लोगों को डाउटफुल था, लेकिन इसका सबसे बेस्ट प्रैक्टिकल एप्लीकेशन जब मार्केट में आया, then everyone kept quiet and they understood that domain theory must be correct. How I wonder whether your generation knows about it, because मैं इतने साल से सिखा रहा हूं, तो जो पहले के स्टूडेंट्स थे उनको ये पता था, आपको शायद ये पता भी नहीं होगा. आपके घर में अगर है तो have you heard of this particular device any time?
यस सर,
ऑडियो कैसेट पुराना डिवाइस है. जब
रेडियो
हम लोग
में लगा
हाँ
के
ऑडियो
या
वीडियो कोई भी आप समझ लो, दोनों में से समझ लो, ऑडियो और वीडियो. ऑडियो इज फॉर म्यूजिक ओनली, वीडियो इज वी यूज्ड टू वॉच फिल्म्स. सीडी से पहले का ये मीडियम था. अभी सीडी भी शायद आपकी जनरेशन ने ज्यादा देखा नहीं, बिकॉज यू आर ऑल MP3. सो ऑडियो कैसेट्स में एक सिंपल था कि दे यूज्ड टू हैव अ कैसेट लाइक दिस and there used to be spools on this one, and then we used to have on this part a film which was rotating. और इसमें ऊपर से इस तरह से वे इसको हम लोग टेप कहते थे, टेप या फिल्म used to go round like this and used to get wound. ये जो टेप हम लोग देखते हैं, ये टेप यूजुअली होता है पॉलीएस्टर का, पॉलीएस्टर टेप या फिर टेरिलिन जिसको कहते हैं, ये टेरिलिन का टेप होता है. अभी ये जो टेप है, इट इज यूज्ड टू बी अ ब्लैक कलर टेप और थोड़ा ब्राउनिश कलर का होता था. इस पे ऑडियो रिकॉर्डिंग, वॉइस रिकॉर्डिंग होती थी. what is the principle of this? This used to be covered with chromium oxide compound, which is basically a ferromagnetic substance. जब हम लोग ब्लैंक कैसेट जिसपे कोई भी रिकॉर्डिंग नहीं है लेके आते थे, तो उसपे पार्टिकल्स कुछ इस तरह से रहते थे, एब्सोल्यूट रैंडम, कैसे भी उस पे रहेंगे. जब हम लोग इसी को आवाज रिकॉर्ड करते थे या म्यूजिक रिकॉर्ड करते थे, सो द रिकॉर्डिंग यूज्ड टू बी डन ऑन दिस. What we see here is the alignment. So ये जब हम लोग ऑडियो कैसेट रिकॉर्डर में रखते थे, यहाँ पे एक ऊपर रिकॉर्डिंग, इसको कहते थे रिकॉर्डिंग हेड, which used to convert audio signal into electrical signal, electrical signal into magnetic. तो audio to electric, electric to ferromagnetic, and it used to print on this particular thing. जब भी हम लोग इसको प्ले करते थे तो ये रिवर्स में जाता था और हम लोग को ऑडियो सुनाई देता था गाने का. दैट वाज अ मैकेनिज्म यूज्ड. दिस एंटायर थिंग इज बेस्ड ऑन द डोमेन कंसेप्ट. ये जो आप देख रहे हो ये डोमेन्स है विच आर एब्सोल्युटली नॉट अलाइंड विद एनीथिंग. और जब हम लोग म्यूजिक रिकॉर्ड करते थे तो ये अलाइनमेंट होती थी. व्हेन वी यूज्ड टू रीप्ले इट, वही ऑडियो फिर से सुनाई देता था. सो दिस होल थिंग, द इंस्ट्रूमेंट ऑडियो कैसेट, इसी को वीडियो के फॉर्म में जब होता है तो थोड़ा फॉर्मेट अलग होता है, बट बेसिक थिंग इज ऑफ डोमेन कंसेप्ट ओनली. सो ये जो डायग्राम आप देख रहे हो उसी तरह का डायग्राम है, वेयर द डोमेन्स इंडिकेट द प्रेजेंस ऑफ मैग्नेटिक फील्ड. प्लीज गो थ्रू दिस होल थिंग. इसमें जो लास्ट का एग्जांपल आप देख रहे हो CrO2 इज व्हाट दे यूज्ड टू यूज ऑन ऑडियो कैसेट्स. प्लीज रीड अप द होल थिंग. शायद फिजिक्स के बुक में आप लोग ये ज्यादा करोगे सब्जेक्ट में, शायद किया भी होगा, पता नहीं मुझे. You can see the second last paragraph. The order of domain remain even when the magnetic field is removed. इसलिए तो ऑडियो कैसेट एक बार रिकॉर्ड करके हम लोग बार बार सुन सकते थे, डोमेन निकल नहीं जाता है. That sound remains there only. जब हम लोग स्कूल में थे और ऑडियो कैसेट सुनते थे तो उसमें एक हमेशा करना पड़ता था कि ऑडियो कैसेट के कभी भी नजदीक आप मैग्नेट को नहीं लेके जाना चाहिए. External magnet, when goes near an audio cassette, the recording is gone because it disturbs the domain. हम लोग ये स्कूल में एक्सपेरिमेंट भी करते थे ऐसे. पुराना कैसेट कोई जो सुनने का नहीं है तो हम लोग उसको मैग्नेट लेके जाते थे उसके करीब एंड वी यूज्ड टू ब्रश द मैग्नेट ऑन इट. फिर उसको प्ले करके देखना तो आवाज पूरा डिस्टर्ब हुआ रहता था. वी कैन नॉट इरेज इट इजीली बट इट यूज्ड टू गेट डिस्टर्ब्ड. With digital electronics, your generation has lost all that fun. You have funs only with respect to apps. So these three magnetism type you have already heard. We have just taken in detail. Now we come to something which you have never heard before. Anti-ferromagnetism. This will have totally a zero magnetic moment. लेकिन आप देखोगे तो सब्सटेंस में काफी सारे अनपेयर्ड इलेक्ट्रॉन्स रहेंगे. Now this is something contradictory. Whenever large number of unpaired electrons are present, it should actually work as ferromagnetic, but still it functions as anti-ferromagnetic. The reason is everything has similar to ferro, but the domains get arranged in such a manner that they cancel each other, and that is why the overall magnetism is cancelled. ऐसे सब्सटेंस बहुत कम है नेचर में. आपके सभी बुक्स में मिलके एक ही एग्जांपल है MnO. I will explain this with a diagram after some time. Watch this one. Ferrimagnetism. Ferri. This will contain also large number of unpaired electrons, but overall magnetic moment will be poor. And you can compare it something like paramagnetism. मतलब नंबर ऑफ इलेक्ट्रॉन्स देखोगे तो लगेगा ये तो फेरोमैग्नेटिज्म होना चाहिए, लेकिन ओवरऑल वैल्यू बहुत कम रहेगी उसकी. So that we call as ferrimagnetism. Here the magnetic domains will be arranged in a little random manner. So let us see this example over here. Now watch this. ये diagram NCERT का है. This explains everything. Domains are exactly aligned. First diagram. This is ferro. Domains are exactly cancelling each other. Up, down, up, down, up, down. Anti-ferro. Up, up, down, up, up, down. तो इसमें इतने सारे डोमेन्स है, लेकिन इसमें से परहैप्स ये सेकंड और थर्ड एक दूसरे को कैंसिल कर रहा है. लास्ट ये दोनों एक दूसरे को कैंसिल कर रहे हैं. तो ऑल्दो देयर आर सो मेनी डोमेन्स, 4 of them are cancelled, remaining are resultant only 2. That is called ferrimagnetism. यहां तक किसी को कुछ भी डाउट हो? जेई और नीट के लिए आपको एग्जांपल्स सभी बाय हार्ट होने चाहिए. That is what the maximum ask in exam. Some other examples I am doing over here. जैसे वो डी ब्लॉक एलिमेंट का आपको एक ट्रांजिशन एलिमेंट का एक स्लाइड दिखाया था मैंने, वैसे ही ये जेई के बुक्स में एक स्लाइड है. कौन से पैरामैग्नेटिक है, कौन से एंटी फेरो, इसका एक जनरल लिस्ट है. अप टिल नाउ नॉट आस्क्ड इन एग्जाम एनीवेयर. एनीबॉडी नोज अबाउट क्यूरी टेम्परेचर? सुना है फिजिक्स में? ये पूरा फिजिक्स का ही कंसेप्ट है. एनी आइडिया फिजिक्स में किया है क्यूरी टेम्परेचर? किसी को याद है जिन्होंने किया है? जो लोग ये सर बोल रहे हैं उनको थोड़ा याद है या खाली नाम ही सुना है?
सर मतलब अगर टेम्परेचर बढ़ा है ना
हाँ
पैरामैग्नेटिक का,
हाँ
तो सर मतलब वो कन्वर्ट हो जाता है फिर पैरामैग्नेटिक में.
correct, that's correct. They have whatever we have seen right now, ferro, anti-ferro, ferri, whatever, they all can transfer to paramagnetism. Remember this first sentence, very important. Ferro, anti-ferro या ferri all can transform to lower stage paramagnetism due to high temperature. For example, Fe3O4, which is ferri, at 850, if you keep it, heat it at 850, it will become paramagnetic. So ferromagnetic material have a temperature above which no ferromagnetism is observed. That is what is known as Curie temperature, right? So उसके जगह पे मतलब no ferromagnetism is observed का मतलब है it will convert into paramagnetism. That is called Curie temperature. Just small notes है, इसमें कोई ज्यादा डिटेल नहीं है. अच्छा, हैव एनीबॉडी हर्ड अबाउट दिस पीजो इलेक्ट्रिसिटी? सुना है कहीं पे, देखा है कहीं
some
पे?
quads का है ना?
Yes, the quartz clocks are working on piezoelectricity. Now, when you have insulators, the electrons do not go from one point to another because obviously they uh, they have large band gaps, so they cannot migrate anywhere. So we call them insulators. But they can create dipoles if you shift the charges. Dipoles can be produced. And besides this, there might be permanent dipoles also. And this permanent dipole production is called piezoelectricity. The word piezo in Latin language means pressure. So we are creating a pressure to create electricity. Now these materials can be used in transducer devices. That means examples you can see are microphone, ultrasonic generators, sonar detectors, and as we said initially, the most common application जो सबसे लास्ट में आपको दिखेगा is quartz clocks. So the clocks include the daily हम लोग के घर में जो clocks होते हैं, wall clocks, they all work on piezoelectric principles. We don't have any much details of this, just a small information, bit of information. ये सब आपको जेई और नीट के बुक्स में दिखेगा. GTB of course doesn't have all these things. Then another information on superconductivity. I hope everyone knows in these years superconductivity, where the flow of electricity will happen with conductor having no resistance at all. 0 ohm resistance. Of course, up till now, superconductivity at room temperature is not possible. Some of the superconductors which are mentioned in the JE books, NEET books are like this. जो टेम्परेचर पे वो सुपर कंडक्टर बनते हैं, that is the first column. The scientist called Owens, Kamerlingh Owens, discovered superconductivity in mercury. That was too low temperature, 4 Kelvin. जितना हाई टेम्परेचर उतना वो कन्वीनियंट होता है. अभी आप ये जो सब कॉम्प्लिकेटेड सब्सटेंस यहाँ देख रहे हो, ये सब कोई ना कोई फॉर्म में यूनिट सेल्स होते हैं. जैसे आपका कोई तो सेल होगा फेस सेंटर्ड क्यूबिक, कोई होगा बॉडी सेंटर्ड क्यूबिक, कोई इससे भी थोड़ा कॉम्प्लिकेटेड. तो ये सब सब्सटेंस वहां पे होते हैं. When you study, especially our PCM students, when you go to engineering first sem, in all the branches first semester is similar. तो आपको ये सब बहुत सारे सब्सटेंस का स्ट्रक्चर स्टडी करना होता है. So there you need to know this FCC, BCC unit cell concept very well. तो फॉर एग्जांपल आप ये अभी देखोगे BaKBi, तो शायद बेरियम might be present at the corners, potassium is at the face centered, bismuth body center, something like this. So ऐसे हर एक के स्ट्रक्चर बहुत सारी जो आपके सिलेबस में रहते हैं, you need to remember them. लास्ट पॉइंट जो जीटीबी में एचएससी में लास्ट ईयर तक था, ये साल कैंसिल किया है और एनसीईआरटी में ये अभी तक है. मेजरमेंट बाय गाउस मेथड. You know, Gauss method basically was discovered to measure magnetic susceptibility. जो हम लोग मैग्नेटिक मोमेंट है उसको डिस्कवर करने के लिए ये साइंटिस्ट ने मेथड निकाला. उसका जो मेथड है बेसिकली वो इस तरह से दिखता है. बहुत सिंपल मेथड ही डिस्कवर्ड. He took a balance, two-pan balance, but on one side, magnetic substance is kept in a powder form, surrounded by electric field. On the other side, there will be a simple weight. जैसे आपका सब्जी वाले के पास रहता है वैसे वेट रहता है यहाँ पे. और इसके दोनों के बिहेवियर से Gauss discovered a method whether a given substance is diamagnetic, ferromagnetic और paramagnetic. ये डिस्कवर करने का सबसे ओल्डेस्ट टेक्निक इज दिस वन. अभी जो ये इंस्ट्रूमेंट्स है ये अभी करंटली भी मार्केट में मिलते हैं लेकिन डिजिटल फॉर्म में मिलते हैं. इट्स स्टिल कॉल्ड गाउस बैलेंस ओनली, लेकिन अभी डिजिटल फॉर्म में. आप यू कैन गो ऑन इंटरनेट एंड चेक, यू गेट फोटोग्राफ्स ऑफ दिस गाउस बैलेंस ऑल्सो. लेकिन हम लोग जो कर रहे हैं इसलिए यहाँ लिखा है मैंने ट्रेडिशनल मेथड. अभी जो है वो कंप्यूटराइज्ड मेथड आता है. व्हाट इज हिज मेथड, लेट अस सी. अगर डायमैग्नेटिक सब्सटेंस है तो आपका अरेंजमेंट कुछ इस तरह से होगा. ये आपके पास मैग्नेट है और जब आप डायमैग्नेटिक सब्सटेंस मैग्नेटिक में रखोगे इट विल गेट रिपेल्ड. तो ये मैग्नेटिक सब्सटेंस इलेक्ट्रोमैग्नेट से रिपेल होगा, उससे ऊपर की तरफ मतलब दूर चला जाएगा। अगर ये दूर जा रहा है तो आपका ये वेट नीचे की तरफ आएगा। यू विल फाइंड अ बैलेंस पुली हैविंग लाइक दिस। This movement tells you it is a diamagnetic substance. For para and ferro, observation is similar. You can see paramagnetic substance will get pulled, attracted towards the magnetic field. Because of this, the weight वाला जो side है वो ऊपर की तरफ move होगा. So इसका exactly opposite thing यहाँ पे होगा. Only difference para में ये difference थोड़ा कम होगा. In ferro, the movement will be too much. So this is the method called Gauss method of determining magnetic property. I hope the
So
topic
this is only for identification, ना?
only for identification. अभी इसमें modifications है, इसमें आप लोग magnetic moment भी find कर सकते हो। जो modern आजकल जो instruments आते हैं, we have much advanced instrument than that. आपके syllabus में simple वाला रखा है उन्होंने।